Hi everyone, in this video we're going to introduce concavity and the second derivative test. Here are the goals of this section. We're going to see what are concavity and the inflection points, and to know how to find the intervals where a function is concave up and concave down, and to know how to find local maximums and minimums using the second derivative test. Now, the concavity can tell us which direction does graph curve. So what does this mean? We know if a function is increasing, then the graph, it could be like this, or it could be like this, right? So both of them, the function are increasing. Now the concavity of the function gonna tell us which one does the curve, or which one does the graph of the function gonna be. So if the graph looks like this, if the curve of the function looks like this, we call this as a concave upward or concave up. If the curve looks like this, we call it concave down. So concave up, you can think concave up as a smile face, and a concave down is a sad face, right? And in some textbooks, another way to think concave up and concave down is when it is concave up, we call it hold water. And when the curve is concave down, we call this as spill water. Spill water. Now the formal definition of concavity is given here. If we let function f(x) be differentiable on an open interval I, so that means the derivative of the function f(x) exists everywhere on this open interval. And if the graph of the function lies above all of its tangent lines on this open interval, then we say the function f is concave up on I. And if the graph of f lies below all of its tangent lines on the interval I, then we say the function is concave down on this interval. So according to this definition, this function, it is a concave up because, as you can see, all the tangent lines, they are below the graph of the function, and this function is concave down because all the tangent lines are above the curve. Okay, now then let's try this example. Let's use the definition we just started to determine where this function is concave up and concave down. So from A to B, the function is concave up. Because when I draw the tangent line, for example, the tangent line at this point, it looks like this, and the tangent line at this point, it looks like this. oh sorry, this is concave down. Now, as we can see, no matter where I draw the tangent line, the graph of the function is always below the tangent line. So according to this definition, if the graph lies below all of its tangent lines, then the function is called concave down. So the function is concave down from A to B. And from B to C, the function is concave up. And from C to D, it concave down. And from D to E, it concave up. And from E to P, it is also concave up. And from P to Q, it concave down. Okay. Another thing about the concavity is if the first derivative is increasing, then the function is concave up. And if the first derivative is decreasing, then the function is concave down. Okay, so how to understand this? Let me use this example again. We know the slope of the tangent line is equal to the derivative, right? Okay, so if we look at this point, if we look at the point, and the tangent line looks like this. So we can see the slope of this tangent line gonna be negative some numbers. Let's say, for example, it's the derivative is -5. Okay, and for this point, the slope of the tangent line is still be negative, but it is gonna be greater than this one. So this, let's say it's a -3. And for this one, the slope may be -2. And for this one, the slope may be -1. And this probably -0.5. And this one, the tangent line is horizontal, so the slope is 0. And for this one, we can see since the tangent line it rises from the left to the right, so the slope gonna be a positive number. Let's say it's +1, and this is +2, +3. So we can see here the slopes are getting bigger and bigger, right? That means the derivatives are getting bigger and bigger. Now, because the derivatives are getting bigger and bigger, that means the first derivative is increasing. And from the graph of the function, we know it's a concave upward. So that's why we have this result. When the first derivative is increasing, the function is concave up. And let's look at this example. So here, the slopes of the tangent lines are getting getting smaller, because first they are positives, and then they becomes 0, and then it becomes negatives. So in this case, the first derivative is decreasing, and the function concave down. So that's why we have this result. If the first derivative is decreasing, then the function is concave down.